right? What you see here is a common bike engine. It's called an internal combustion engine. Okay, ICE, right? Basically, the petrol engine that many bikes use. Can one of you tell me what basically happens in an engine as we use the vehicle? What happens in an engine? Fine. I got one answer as it converts energy. Okay, that is good. But what form of energy to what form of energy? Let us discuss that. Now we know that an internal combustion engine consumes fuel, okay, petrol. So basically, why we need petrol is because it has energy in it, chemical energy. So what this engine does is it converts the chemical energy of the fuel to what? It first converts it to heat energy. Combustion means combustion of fuel takes place there. Okay. So the fuel kind of gets burnt, and in that process, heat is released. And that heat is converted to mechanical energy. That is what makes the vehicle move. Right. Now, conversion of chemical energy to heat energy that you will learn in chemistry. How much heat can be, or how much heat would be released in a chemical reaction that you must have studied in chemistry for some reactions at least. Now, in thermodynamics, what you learn about is this part, how to convert heat to mechanical energy. That is the uh, like that is a basic discussion that we have in thermodynamics. Okay? Conversion of heat to mechanical energy, or you can also say work. Fine. Can any of you come up with any other examples or any other situations, any other machines? Okay, examples of machines or any situations where heat is getting converted to work or mechanical energy. Any other situation that you can think of? Okay. Consider a pressure cooker. Okay. So let's assume you are cooking rice in it. Now, when you keep it on the stove turned on for some time, you see that the pressure cooker occasionally gives out whistles. What happens there, or what gives rise to that whistle? Basically, the water that is there inside gets boiled, steam gets produced. Okay. When heat is supplied to steam, basically it would expand. Now, inside the pressure cooker, there is limited volume. Fine. So when the pressure becomes too high and the steam can no longer stay inside the pressure cooker, inside the volume of the pressure cooker, what happens is basically due to pressure, the steam will be pushing the walls of the pressure cooker, and not just the walls, it will be pushing the vessel also. But the vessel there has some weight. Okay. Uh, So due to its weight, up to a certain amount of pressure it can withstand. But when the pressure inside becomes too much, the steam will push the weight so hard that it rises up and then steam escapes. And in that process, that whistling sound is produced. So this is also an example of heat getting converted to mechanical energy. Sound is getting produced. Whistle is being pushed up. Okay. When something rises, it means it is gaining potential energy, which is nothing but mechanical energy. Fine. So this is also a very common example of heat getting converted to mechanical energy or work. And this is what we'll be studying in thermodynamics. How heat can be converted to work. Okay, fine. Now, when you supply heat to an object, what happens? We know materials expand on heating. So heat supply can result in expansion. And it also results in a change in temperature, of course. Okay, usually an increase in temperature. When you supply heat, the temperature of an object rises. Now, we had talked about this before. Temperature depends on the energy of molecules, energy per molecule. So, when you supply heat, some part of that heat energy gets stored with the molecules. Okay, the molecules keep some of that energy. That is what results in a temperature rise. Okay, so the part of heat which is getting stored with the molecules, we call that as internal energy. The energy which the molecules have, that is called internal energy. Okay, now it would also result in expansion of the object, whatever it is that you are supplying heat to. When an object expands, it can push the surroundings. Okay, so basically what happens when you push something, you are doing work. Okay, you are exerting a force, and if it results in some displacement, then some work is also being done, right? So in this process of expansion, work can be done. That is the basic idea behind conversion of heat to work. Supply of heat results in expansion, and that expansion, during that expansion, if something is being displaced, work is being done. That is how heat gets converted to work. Okay. And what you see here is very important. If you supply heat to a system, some of the heat gets stored within the system. The remaining heat gets converted to work. This is what we call as the first law of thermodynamics. Mathematically, we write it this way: delta Q. Okay. Delta Q stands for heat supplied to the system. What happens to it? Some of it gets stored within the system. Okay. This is called change in internal energy. The system would already have some internal energy. Molecules will have some energy. If you supply heat, they'll get some more energy. Okay. So that is called change in internal energy. U stands for internal energy. Okay. And some work also will be done, may be done. So this we say is work done by the system. So this is how we write the first law of thermodynamics, or how we apply the first law of thermodynamics. Delta Q is delta U plus delta W. Right. It is very important to know the meaning of these terms. Delta W stands for work done by the system to which heat is supplied. Okay. Anyway, we'll use this a little later. So the fundamental idea behind conversion of heat to work is based on thermal expansion. Okay. When you supply heat, temperature rises, expansion takes place. During that expansion, if something gets displaced, work is done. Okay. Now, you all know we have different states of matter. Basically, the common states that we come across are solid, liquid, and gas. Now, you all tell me, out of solids, liquids, and gases, which do you think will undergo more expansion when some heat is supplied to them? According to uh, like your, uh, I mean, your own idea, you tell me, if we supply heat to these different states of matter, which state of matter do you think expands more? Okay. I got one answer as gases, and that is correct. Okay. Gases have the least amount of intermolecular attraction between them out of all three states of matter. So, any material in gaseous form will expand more easily compared to solid liquid form. So, mostly the system that we use to convert heat to work is a gas. Fine. So to understand how much heat can be converted to how much work, or how exactly heat can be converted to work, we need to first discuss the properties of gases. Okay. And we will be considering something called an ideal gas. We'll be considering something called ideal behavior of a gas. Fine. So we'll first talk about properties of ideal gases. Fine. Now, Why do gases tend to expand more than solids and liquids? Because the intermolecular force of attraction between the molecules is least. Now, when it comes to an ideal gas, what we assume is that there is absolutely no intermolecular force of attraction between the molecules. So that's the basic or first assumption in an ideal gas. No intermolecular attraction or repulsion also. Okay. Next, we know gas molecules are never stationary. They are stationary only when the temperature is 0 Kelvin, absolute zero of temperature. Any temperature greater than that, gas molecules will be moving around, okay, in a container. Now, when you put gas in a container, the actual space filled by the gas molecules will be much lesser than the space available in the container. So, what happens is something like this. Suppose this is the container. Now, assume these are the gas molecules. So, situation will be like this. There will be a lot of empty space in the container. The container won't be completely packed with gas molecules. If it is completely packed, how will they move? Okay. Even if it's a solid, okay. Suppose you take a cube whose side is 1 meter. It doesn't mean the entire volume of 1 meter cube is filled with molecules. There will be empty spaces. Molecules will be vibrating. They will have space between them. Okay. You must be knowing, no, even in a bond, okay, chemical bond between two atoms, there is gap between the atoms. So there is something called bond length. Nothing is present in that gap. Okay, it's empty space, it's vacuum. Fine. So same thing happens with gases also. So when a container is filled with a gas, there will be a lot of free space in the gas. Okay. So when it comes to ideal gases, what we assume is the actual space taken up by the gas molecules is very less compared to the volume of the container. Right? Now see, if a container is filled with gas, we say that volume of gas is equal to volume of container. That doesn't mean container is completely filled with gas molecules. The space up to which these molecules can move is the volume of the container. That is what we mean by volume of a gas. What volume are they free to move within? Okay? That doesn't mean the volume is completely filled with molecules. There has to be space, there will be space. Okay. Now, how is this possible? The actual space taken up by the molecules is very less compared to volume of the container. How is that possible? That is possible if the molecules are very small compared to dimensions of the container. Okay. Next, these gas molecules, they'll be moving around randomly, right? So obviously they will undergo collisions. They may collide with other gas molecules. They may even collide with the container also, walls of the container. Now, whenever these molecules, ideal gas molecules collide, we assume that the collisions that they undergo are elastic in nature. Okay. What is meant by an elastic collision? Basically, whatever deformation occurs during the collision, all of it will be restored. That is what happens in an elastic collision. And in an elastic collision, mechanical energy will be conserved. It won't be converted to other forms of energy. Okay, like we had discussed this in work energy and power. If two objects undergo a collision, there will be deformation happening, there will be restoration also happening. So, in an elastic collision, complete restoration takes place. Okay. So we assume that collisions of ideal gas molecules, be it with other molecules or with the walls of the container, are elastic in nature. Okay. And during these collisions, we assume they obey Newton's laws. Fine. So these are the fundamental properties of an ideal gas, which are important, and based on these only we will discuss or we will derive some relations or formulas for an ideal gas, okay, based on these assumptions. The first thing is that there must be no intermolecular attraction or repulsion. Only when molecules collide, they interact with each other. Interacting means exerting forces. Okay. So ideal gas molecules exert forces on each other only when they collide. Okay. Obviously, during collision, it will be a repulsive force. Otherwise, there will be no intermolecular attraction or repulsion between them. Okay. Next, the actual space filled by the molecules is very small, means there is a lot of empty space in a container filled with a gas. Then whatever collisions the molecules undergo, they are supposed to be elastic. They are assumed to be elastic and they obey Newton's laws. Fine. Next, now you all must have studied the ideal gas equation in your lower classes itself. Basically, ideal gases obey this equation. PV is equal to nRT. P stands for pressure, V is volume of the gas, N is the number of moles, R is the universal gas constant, and T is absolute temperature. This is valid only when temperature is in Kelvin. Okay. Other quantities, other terms, if you want, you can change the units, but temperature unit should not be changed. It must be written in Kelvin itself. Pressure, if you want, you can express it in pascals. If you want, you can express it in atmosphere. You can change the unit. Volume, if you want, you can write in meter cube, centimeter cube. You can change the unit. Accordingly, the other terms units will change, but temperature must always be written in Kelvin. Otherwise, this equation will not be valid. Okay. Now, what we will discuss is how this equation is derived. Why does an ideal gas behave like this, or why does an ideal gas obey this equation? Okay. Let's see. So what we will first do is we will derive a relation between pressure of a gas, okay, and the speed of its molecules. Now, based on speed, we can express kinetic energy. So we can relate pressure to kinetic energy, and energy is related to temperature. Energy of molecules is related to the temperature of molecules. That way, we can relate pressure to temperature. So we'll first relate pressure to speed of gas molecules. Speed will be related to temperature, and thus we will relate pressure and temperature. That is how we will arrive at the ideal gas equation. Okay. This discussion, this derivation is very important. So follow this carefully, all of you. First of all, consider a container. Okay. Let's assume it's a cubical container. See, we could have considered a container of any shape. If it's a cube, the derivation will be easy. So we choose this. Okay. Consider a cubical container of side L. Okay. Side length is L. Fine. In that, let's say there are some gas molecules. Not some, there could be many gas molecules which will be moving around randomly. Let's say mass of each molecule is small m. Mass of all the gas that is present, let it be capital M. Okay. And number of moles, let it be small n. Okay. I am assuming you know what is 1 mole of a gas. 1 mole of anything basically consists Avogadro number of those particles. So 1 mole of a gas consists Avogadro number of molecules of that gas. Fine. Now consider any one random molecule in this. Let's say this one. That molecule could be moving in any direction. Okay. So it could have some velocity in the x direction, some velocity in the y direction, and some velocity in the z direction as well. You have to think of this as a three-dimensional container. Obviously, every container is three-dimensional only. So this molecule, whatever velocity it has, we can resolve it into three components. Now, why are we bothered about components? Basically, what do we want to do? We want to derive a relation between pressure of the gas and the speed of its molecules. Pressure is force per unit area. Now, these gas molecules, due to their random motion, they'll be hitting the walls of the container. Fine. So, whenever they hit the wall of a container, they exert a force on it, they create pressure on it. So, that is how we are going to relate speed to pressure. Fine. Now, this molecule, the particular molecule that we have considered, could be moving in any direction, we don't know. It may be moving completely in the x direction itself, completely in the y direction itself, or somewhere in the xy plane, or it may be having x, y, z, all three components also. So we have no idea how exactly it is moving. Fine. But let's assume this molecule has some x component Vx. Definitely, many molecules will be having velocity in the x direction. Some molecules may not have. Okay, they may have only y components and z components, but there will be many molecules having x components, right? Let's say we are considering one such molecule. Now, due to this velocity in x direction, what this molecule will do is, it will hit this wall of the container. The x component of velocity is what makes the molecules hit these right side and left side walls. Upper wall and lower wall, they will be hit due to the y component of velocity. Front wall and back wall, they will be hit due to the z component of velocity. So it's the x component which takes the molecule towards this wall, this particular wall. Okay. Now let's consider this separately. Suppose the molecule, we assumed molecule's mass is small m, moving with a velocity Vx, that is the x component of its velocity, strikes the wall. Okay, the wall is here. Now I just told you that any collision that an ideal gas undergoes would be elastic in nature. Okay. Now the wall of the container is fixed. Relative to the container only, the molecule is moving with a velocity Vx in the x direction. It may have y component and z component of velocity also, but those components are not going to make the molecule hit this wall. For hitting this wall, it's the x component that matters. Okay, so we are considering only that. Now, in an elastic collision, what happens? Speed of approach is equal to speed of separation. Relative speed of approach is equal to relative speed of separation. Now, the wall is at rest. Okay. So, the speed with which the molecule is approaching the wall is Vx. Then it will rebound from the wall with the same speed Vx after the collision. So, when this particular molecule goes and collides with this wall, this is what is going to happen. Fine. Before hitting the wall, its velocity would be Vx towards right. After hitting the wall, its velocity would be Vx to the left. Speed remains same, direction changes. Okay. Now, our aim is to derive a relation between speed and pressure. Pressure is force per unit area. So, if you can first relate speed and force, then you can relate speed and pressure. Okay. How to relate speed and force? Force is rate of change of momentum. Okay, F is equal to dp by dt or delta p by delta t. Speed or change in speed can be related to change in momentum. Change in velocity can be related to change in momentum. That can be related to force and that can be related to pressure. That is what we are going to do. So based on Vx, we will express, or based on change in velocity in x direction, we will express the change in momentum. From that, we can express force, and from that, we can express pressure. That is the idea. That is a procedure we are going to follow. Okay. Now the mass of the molecule is m. Its velocity is Vx towards right before collision. Just after collision, it is Vx to the left. So before collision, you can say its velocity is plus Vx. And after collision, its velocity is minus Vx. Speed is the same, Vx, but direction has reversed. So if one of them is plus, the other should be minus. Then whenever a collision happens, okay, so during this collision, how much is the change in momentum of the molecule? Change in momentum is final momentum minus initial momentum. After collision, the momentum is minus mvx. Before collision, the momentum was plus mvx. So the change in momentum becomes minus 2 mvx. Okay. Now this is the change in momentum of the gas molecule, right? For change in momentum, a force is needed. Okay. Now, what force caused this change in momentum? The normal force exerted by the wall of the container. So, on this particle, on this gas molecule, a force would have acted to the left. On the wall of the container, a force would have acted to the right. Fine. And from Newton's third law, these will be an action reaction pair. We can say that whatever magnitude of force the molecule experienced, the same magnitude of force the wall would have experienced. Okay. So whatever change in momentum the molecule has experienced, a negative of that the wall would have experienced. So what I mean is momentum delivered to the wall, or you can say impulse delivered to the wall. Okay, change in momentum. Okay, I think that will be better. Whenever an object collides with another object, impulse will be delivered, right? So impulse delivered to the wall basically will be plus 2m Vx. So when a gas molecule collides with this wall with a speed Vx, this is the impulse that the wall experiences. Impulse is nothing but change in momentum. Okay. Now change in momentum divided by the time taken gives you force. Now come back to this picture. This molecule, the particular molecule that we have considered. Okay, let me show one molecule only. Let me erase the others. The particular molecule that we have shown here has a certain component in the x direction, velocity component in the x direction. Now with that velocity component, it will keep moving like this. Hits this wall, then goes back, hits this wall, then goes forward, hits this wall, goes back, hits this wall. So that right left motion is governed by the x component of velocity. Okay, depends on the x component of velocity. Fine. Now the length of the cube was considered as L. Okay. Let's say the molecule has just undergone a collision somewhere here. Now, for it to collide with this same wall again, it will have to travel a distance L backward and again a distance L forward. And for that, it takes some time delta t. After that much time, it will again hit this wall. Okay. So after every interval of this much time, delta t, and see, speed is distance by time, time is distance by speed. So distance divided by speed, L divided by Vx. Okay, not L actually, it has to go L for L backward, another L forward. So 2L divided by Vx. After every interval of this much time, that molecule will collide with this wall. Okay. So this much impulse, 2mvx impulse, will be delivered to the wall after every interval of 2L divided by Vx. Okay, hope this part is clear to all of you. The molecule will collide with the wall when it goes back and again comes forward towards this wall. Okay, for that to happen, it has to travel a distance of L plus L to L. And with what speed does it travel in this direction? Vx. Okay, distance divided by speed gives you the time it takes. So after every interval of 2L by Vx, an impulse of 2mvx will be delivered to the wall. So impulse means change in momentum and interval is delta t. If you know delta p and delta t, dividing them will give you the average force acting on the wall. Or I can say average force exerted on the wall by one molecule. We have only considered one molecule so far. So that will be change in momentum is 2m Vx divided by the time after which this much impulse is delivered is a regular interval of 2L by Vx. So effectively, how much does that become? M Vx square divided by L. That's the average force exerted by one molecule on that wall of the container, where m is the mass of that molecule, Vx is the x component of velocity of that molecule, and L is the length of the container. Okay. Now, if one molecule is exerting this much force, see, it's not just that one molecule which hits the wall of the container and creates a pressure on it. No, other molecules also will be hitting it. Okay. So we have to consider the force exerted by all the molecules on this wall of the container. Therefore, or uh, okay, fine. Let's consider force exerted by all molecules. Therefore, average force exerted by all molecules. Okay. All means, let's say there are n number of molecules or n naught number of molecules would be how much? N naught multiplied with mvx square by L. One molecule exerts a force of mvx square by L, then n naught molecules will exert a force of n naught times mvx square by L. But there is a catch here. The catch is with Vx. All molecules are identical. We are considering one gas only, so the molecules are identical, their masses will be equal. L is the length of the cube, that will not change anyway. But what is Vx? Vx is the x component of velocity of the gas molecule. Now you all tell me, okay, and I want answer from all of you very quickly. Do you think every molecule, every gas molecule in a container will have the same x component of velocity? Okay, I got two answers and I got two opposite answers. One of you saying no, not every molecule, I mean, all molecules won't have the same x component of velocity, and another answer saying yes, all molecules will have the same x component of velocity. Now, the one who said yes, if you think all molecules have the same x component of velocity, indirectly you are also saying all molecules will have the same y component of velocity, all molecules will have the same z component of velocity also. That means you are indirectly saying all molecules will have the same velocity. Why? Why will all gas molecules which are free to move randomly have the same velocity? They won't. Okay, one molecule may be going this way, another molecule could be going this way, one molecule could be going up, another could be going down, some other molecule could be going in a random direction. Okay, not could be, will be. Gas molecules will be moving randomly. Okay, they have no preferred direction of motion. Fine. So all the gas molecules will not have the same x component of velocity. So what are we writing now? We are writing an expression for average force exerted by the molecules. No, we got average force exerted by one molecule as this much. Now, if you want to extend that to all molecules, what you have to do is total average force should be expressed like this. Total number of molecules, mass of each molecule, length of the container, these are fixed. You will have to take average of Vx square of the molecules. Okay. Angular brackets indicate average of that quantity. So how do you read this? Average of Vx square. For some molecules, Vx, the x component of velocity could be completely zero. For some, it will be non-zero. Not for some. For many, it will be non-zero, but for some, it could be zero also. Okay. So we will have to average Vx square of all the molecules. Then only we can get the average force. Okay. Now see, generally, the velocity of an object or a particle is expressed like this: Vx I cap plus Vy j cap plus Vz k cap. The velocity has all three components. Now, it's not necessary that all three components are equal. Okay. Now, the magnitude of velocity, which is what we call as speed. Okay. By definition, magnitude of velocity is speed. We can write it as V, can be written as under root Vx square plus Vy square plus Vz square. Now you square on both sides. Square of the speed becomes Vx square plus Vy square plus Vz square. Now, for some molecules, the x component may dominate. For some molecules, the y component may dominate, and in some molecules, the z component may dominate. But see, we had discussed this before itself. Temperature is a measure of energy of the molecules, right? Now, at a particular temperature, all molecules will have the same energy. If particular molecule has more energy, it will be at higher temperature. Less energy, lower temperature. If you are saying all molecules are the entire gas is at one temperature, it means all molecules have the same amount of energy. At least, uh, like roughly, we can say that. So what we can say is that this sum will be same for all molecules. Some of them may have higher x component, lower y component. Some of them may have lower x component, higher y component, but the sum of all three is going to be the same for all molecules. Okay. Now, we also know that there is no preferred direction of motion for the gas molecules. So what we can say is, see, v square, the square of speed, is the sum of vx square plus vy square plus vz square. That is from the definition of velocity. Okay. Then average of v square, okay, I'll write it in angular brackets. Average of v square will be average of vx square plus average of vy square plus the average of vz square. This is basic mathematics. Okay. When one quantity is the sum of three other quantities, then the average of this quantity will be the sum of averages of the other quantities. Okay. Now, for some molecules, Vx will be dominating. For some molecules, Vy will be dominating. For some molecules, Vz will be dominating. But when you average them for all the molecules, these three must be equal because the gas does not have a preferred direction of motion. So on average, for all molecules, if you see, the average of Vx squares should be equal to the average of Vy squares and should be equal to the average of Vz squares. That is what I'm saying. For one molecule, Vx, Vy, Vz need not be same. But if you average Vx for all the molecules, average Vy for all the molecules, average Vz, okay, or let me be more correct. If you average Vx square of all molecules, Vy square of all molecules, and Vz square of all molecules, those averages should be same. Okay, because if the averages are not same, suppose Vy square is dominating, it means the gas as a whole, okay, the set of molecules has a preference towards y direction. Why will the gas have a preference towards any direction? No, gas moves randomly. So all these averages will be equal. Since all the averages are equal, you can say that this is equal to 3 times the average of Vx square. You can also say it is equal to 3 times the average of Vy square or 3 times the average of Vz square. Okay. So the average of square of speed of gas molecules is 3 times the average of square of x component. So you can say that 3 times average Vx square is average V square. Now send the 3 that side. So the average of Vx square becomes 1/3 the average of V square of all the molecules. And this we are going to substitute here, the average of Vx square. So going back to what we wanted to derive, basically, we wanted to derive an expression for pressure, okay, or a relation between pressure and speed. So we can say that the total average force experienced by one wall of the container is number of molecules multiplied with mass of each molecule multiplied with, we had average of Vx square. I'll now write this as average 1/3 the average of V square divided by L. This is the total average force experienced by the wall of the container. Okay. Now, if you know the average force that a wall experiences, you can tell average pressure that the wall experiences. Therefore, average pressure. How do we derive pressure? Force divided by area. Now we considered a cubical container. What will be the area of any wall of that container? L square. So force is N naught M average V square divided by 3L. That is force. And divided by area again. So divided by L square. So effectively it becomes 3L cube. Okay. L multiplied with another L square effectively becomes L cube. Now L cube is nothing but the volume of the container. We considered a cube of side L. So L cube becomes the volume. We'll write this as capital V. Okay. Small v stands for speed of gas molecules. Capital V stands for volume of gas. Volume of gas or volume of container also you can say. Okay. Volume of container itself is the volume of gas. Okay. So we get pressure on the wall of the container is 1 by 3 N naught. N naught is the number of molecules. M is the mass of each molecule multiplied with the average of the square of the speed divided by volume of the container. Okay. So you can write PV is equal to 1 by 3 small m capital N naught average of V square. This is how we can relate the pressure of a gas to its speed, to the speed of its molecules. Okay. This is what we call as kinetic interpretation of pressure. Means relation between speed of molecules and pressure of the gas. Okay. There is another way also to write this. Here small m is the mass of each molecule. N naught is the number of molecules. Let us express this in terms of moles. Okay. Let small n be the number of moles. How do you calculate number of moles? Small n, number of moles is number of particles divided by Avogadro number, right? Na is Avogadro's number. That's 6.023 into 10 power 23. Okay. Therefore, you can write number of particles or number of molecules as number of moles multiplied with the Avogadro number. Okay. Therefore, the equation changes to PV is equal to 1 by 3 small m. In place of N naught, I'm now going to write small n multiplied with Avogadro number multiplied with the average of V square. Okay. Now, small m is the mass of one molecule. Now, you all must have studied something called molar mass, which is basically mass of 1 mole of molecules. Okay. Mass of 1 mole. If it's molecules that you consider, you call it as molecular mass or molecular weight of the gas. So, what is molecular weight? It is the mass of 1 mole of molecules. For example, we say molecular weight of water is 18 grams. Okay, molecular weight of H2O is 18 grams. I think, okay, some of you may be calling it as molecular mass also. That's fine. We say it is 18 grams. What does that mean? It means 1 mole of H2O weighs 18 grams. 1 mole means what? Avogadro number of molecules of H2O will weigh 18 grams. It doesn't mean one molecule of H2O weighs 18 grams. That is ridiculous. Okay. So molecular weight is basically mass of 1 mole of molecules. How do you get mass of 1 mole? Mass of each molecule, mass of each molecule is small m. Mass of each molecule multiplied with Avogadro number gives you the mass of 1 mole, which is molecular weight. So small m, mass of each molecule multiplied with Avogadro number put together becomes capital M. What is capital M? Molecular weight of that particular gas. Therefore, we get PV is equal to 1 by 3 capital M N average of V square. Okay, this equation is very important. Based on this, we can derive the ideal gas equation. PV is equal to nRT. So far, we have related pressure to speed of gas molecules. PV is equal to 1 by 3 mn v square. Okay. So let's go through this derivation once again. So what we considered is a box, a cube, in which there is an ideal gas present. Then we looked at one molecule. We considered one molecule. We gave it some speed, some components of velocity we assigned. Because of its velocity, because the molecule is moving, it will be hitting the walls of the container. So we considered one wall of the container, the right side wall. To hit the right side wall, it's the x component of velocity which matters. Okay, so we assigned some x component of velocity. We assumed the molecule hits the wall and rebounds. When it hits and rebounds, we found out change in momentum, delta P. Per molecule, how much is the change in momentum? We found out. That same impulse would be imparted to the wall. So we know how much impulse one molecule will impart to the wall of the container. And impulse divided by time gives us the average force that it exerts. That was the next thing we found out. And if you know average force exerted by one molecule, you multiply it with the number of molecules, you can tell the average force exerted by the entire gas on that wall of the container. But there was a problem. All molecules won't have the same x component of velocity. So we had to average the x component of velocity. And instead of sticking to the x component, we converted x component, or we expressed x component in terms of the overall speed of the molecule. Okay, so average of Vx square will be one third the average of V square. That is what we substituted here. So we got an expression for total average force experienced by one wall of the container divided by area. You will get an expression for average pressure exerted by the wall of the, average pressure exerted on the wall of the container. So that is how we are relating pressure of an ideal gas to the speed of its gas molecules. Okay, fine. Next, we have to relate speed to temperature. Okay, let's see how that is done. Before that, we first have to discuss something called degrees of freedom of a gas, of an ideal gas. Okay, we denote this by the symbol small f. Degrees of freedom basically mean the number of independent ways in which a molecule can store energy. Okay, that is what we call as its number of degrees of freedom in which a molecule can store energy. Now, there are different types of molecules. Some of them are monoatomic, atom itself is the molecule. Some of them are diatomic. And beyond diatomic, we generally call it as polyatomic. Okay. Three atoms, four atoms, five atoms, any number of atoms greater than two, we call the molecules as polyatomic. Now, depending on the atomicity, okay, number of atoms in the molecule, the degrees of freedom will vary. Okay. First, let's consider a monoatomic gas. Now, consider one molecule of a monoatomic gas. The atom itself is the molecule then. Okay, it doesn't bond with anything. Okay. Now, in an ideal gas, molecules don't interact with each other. So this molecule is not going to interact with any other molecule. If there's no interaction, there is no potential energy. Okay, now we have discussed this in mechanics that potential energy arises due to interaction between molecules of a system. Okay, or particles of a system. When you change the arrangement of a system, its potential energy changes due to the action of conservative forces. But this molecule doesn't even have any attractive or repulsive forces with other molecules. So there is no question of it having any potential energy. Okay, then the only kind of energy it can store is kinetic energy, right? Now this molecule could have an x component of velocity, Vx, could have a y component of velocity, Vy, and it could have a z component of velocity, Vz. Now we consider these as three independent motions of the particle. Okay. So due to motion along x direction, it can store some kinetic energy. And due to motion in the y direction, it can store some kinetic energy. And due to motion in the z direction also, it can store some kinetic energy. And velocity basically makes the object translate. Angular velocity makes the object rotate. Linear velocity makes it translate. So we say that a monoatomic gas molecule has three different ways of storing energy. See, it cannot store potential energy, first of all. It can store kinetic energy. And kinetic energy due to x component of velocity is completely unrelated to kinetic energy due to y component because x, y are completely independent. Okay, they have a 90-degree angle between them. X component, y component are independent. Similarly, z component. So we say that there are three different ways in which it can store translational kinetic energy. So we say that it has three translational degrees of freedom. Okay, it can store translational kinetic energy half mv square, and there are three independent ways in which it can do that. So we say that it has three translational degrees of freedom. What about rotational kinetic energy? We know that kinetic energy is of two types, translational, rotational. Translational is half mv square. Rotational is half I omega square. Okay, we had discussed this in rotational mechanics. I stands for moment of inertia. Now, it's a monoatomic gas. There's only one particle. There's no system. Okay. The moment of inertia of a single particle when it rotates about itself is zero. Okay. Because the particle lies on the axis of rotation. What is the formula for rotational kinetic energy? Half ICM omega square. If there's only one particle in a system, no, that particle itself will be the center of mass. So if you consider an axis passing through the center of mass, it's automatically an axis passing through the particle. Then how can it have any moment of inertia? It cannot, because moment of inertia is given by mass multiplied with square of distance from the axis. If the particle lies on the axis, it won't have any moment of inertia. So it cannot have any rotational kinetic energy. Therefore, a monoatomic molecule can only store translational kinetic energy in it. Okay. And there are three independent ways in which it can do that. So we say that a monoatomic gas molecule has three translational degrees of freedom, and those are the only degrees of freedom that it has. So for a monoatomic gas, F is 3. It has three independent ways in which it can store energy. What kind of energy? Translational kinetic energy is the only energy that it can store. Okay. Next, consider a diatomic gas. Means the molecule is made up of two atoms. Okay. Let these be the two atoms of the molecule. The two atoms will definitely have a bond between them. Within the molecule, atoms will be interacting. Otherwise, how will they form a molecule? Okay. They must have a bond. Only then a molecule will be formed. So within the molecule, interaction will be there. But from one molecule to another molecule, there won't be any interaction. So this is one molecule of the diatomic gas. You consider another molecule of the diatomic gas. That molecule and this molecule won't have any interaction between them. Okay, those are the properties of an ideal gas. In an ideal gas, molecule-molecule interaction is not present. Okay. Now, if you consider a diatomic gas like this, its center of mass will be somewhere here. It won't coincide with any of the atoms. Okay, center of mass will be present somewhere here. Okay, but a diatomic gas, since there are only two atoms, they are like two particles. You can draw a line connecting those two particles. You can always draw a line connecting 2 points. Fine. Now this molecule can be moving around. So the molecule as a whole can have an x component of velocity. It can have y component of velocity. It can have a z component of velocity as well. So there will be translational degrees of freedom. The molecule can translate, it can move. Okay. So a diatomic gas definitely has three translational degrees of freedom. It can store energy in the form of translational kinetic energy half mv square. That is what we mean. And because Vx, Vy, Vz are independent, there are three different ways in which it can store kinetic energy, translational kinetic energy. Next comes rotational kinetic energy, half I or half ICM omega square. This time, the particles don't lie at the center of mass. Okay, the two particles have some gap between them, that is bond length. Between them will be the center of mass. Now you can imagine axis passing through the center of mass, y-axis, x-axis, and then z-axis. Fine. You can see that x-axis is the axis on which these two particles are lying. So about x-axis, its moment of inertia will be zero. If particles lie on the axis, they won't contribute to moment of inertia. But about y-axis, there will be non-zero moment of inertia. About z-axis also, there will be non-zero moment of inertia. Therefore, it can store rotational kinetic energy about y-axis. It can store rotational kinetic energy due to rotation about z-axis as well. So it has two rotational degrees of freedom. Okay, means there are two independent ways in which it can store rotational kinetic energy. That is what we mean by two rotational degrees of freedom. Okay, so there are three independent ways in which it can store translational kinetic energy and two independent ways in which it can store rotational kinetic energy. Okay, so five ways in which it can store kinetic energy. So these will contribute to 5 degrees of freedom. Fine. What about potential energy? Now, potential energy arises when there is interaction. A monoatomic gas does not a monoatomic gas molecule does not interact with anything, but a diatomic gas molecule interaction is not there. Let it not be there, but within the molecule atom atom interaction is there. So due to that interaction, storage of potential energy is possible. Fine, it's like two blocks connected by a spring. If the two blocks come closer and compress the spring, spring can store potential energy. If it expands also, spring will have potential energy. A single block cannot have that kind of potential energy, but two blocks connected by a spring can have elastic potential energy in that system. Okay, so diatomic molecules can store potential energy. But when will that be useful? Only when that potential energy can be released. Or it can be some additional potential energy can be stored, or if it can be released only, it is useful. Suppose two blocks are connected by a rod, then there won't be any elastic potential energy between them. If they are connected by a spring, there can be elastic potential energy between them. It can be stored, it can be released. But if they are connected by a rod, that cannot happen. So same thing here also. If it is a rigid diatomic molecule, rigid means the two atoms are not allowed to come close or go away from each other. They have a fixed distance. If it is a rigid diatomic molecule, you don't have to bother about its potential energy, because if the atoms cannot come close or go away, you cannot store extra potential energy or release potential energy from that molecule. Then it's useless considering potential energy. Okay. So if it's a rigid diatomic gas molecule, then it can only store kinetic energy. It can't store additional potential energy. If you cannot compress the spring, you cannot store extra energy in it. So same idea you can apply here also. If the bond cannot be compressed, okay, if the distance between the atoms cannot be changed, if it is fixed, you can't store extra potential energy in that system. So if it's a rigid diatomic gas molecule, then it can only store kinetic energy. It can store translational kinetic energy in three different ways and rotational kinetic energy in two different ways. So it will have 5 degrees of freedom. What if the molecule is non-rigid? What if the atoms are allowed to vibrate? Then it can store potential energy also. Okay, due to that, in that vibration, potential energy can be stored, can be released, and due to vibration, some more kinetic energy also can be stored. So it will have additional degrees of freedom, additional ways in which it can store energy. Two additional ways will be there. Okay, when a bond is allowed to oscillate, two additional degrees of freedom will arise. Okay? But in your syllabus, you only consider rigid molecules. But you need to remember, what if the molecule is flexible? Okay, so we are going to take degrees of freedom of a diatomic gas as 5 itself. We will assume it can only store kinetic energy because we assume the molecule to be rigid. But they may ask you some conceptual questions like what if it is not a rigid molecule? So if it is not rigid, if molecule is non-rigid, then each bond can have, not can have, will have two additional degrees of freedom. Two additional degrees of freedom means two additional ways in which it can store energy. So in that vibration, potential energy can be stored, and in that vibration, atoms are moving means they have kinetic energy. That vibrational kinetic energy also can be stored. So potential and vibrational kinetic energy, two additional degrees of freedom will come. Okay, but as I said, we'll consider the molecules by default. We'll consider them to be rigid. We are only going to consider 5 degrees of freedom for a diatomic gas. Okay. Next, polyatomic gas. Now consider a molecule which consists many atoms like this. Okay, 3, 4, or anything more than that. Anything more than 2. Now the center of mass of this system would lie somewhere here. Through the center of mass, if you imagine axis, one x-axis, y-axis, z-axis. You can clearly see that there is no particular axis on which all the particles lie. Two particles may lie on an axis, three particles may lie on one axis, but all particles won't lie on one axis. It's a non-linear molecule. Okay. Then this kind of a molecule, see, it can definitely translate, it can move around. So it will have translational kinetic energy, and it can have translational kinetic energy due to velocity in the x direction, due to velocity in y direction, and due to velocity in z direction. So it will have three translational degrees. Next is rotational kinetic energy. Since there is no particular axis on which all the atoms lie, it will have significant moment of inertia about x-axis. It will have significant moment of inertia about y-axis and also about z-axis. So it can have three rotational degrees of freedom as well. Okay, it will have. Okay, so three translational degrees of freedom and three rotational degrees of freedom. So the total number of degrees of freedom for a polyatomic gas will be 6, provided it is non-linear. If it is linear, if there is one particular axis on which all the atoms can lie, then it will have 5 degrees only. Because along that particular axis, moment of inertia will become insignificant. But if it is non-linear, it will have 6 degrees of freedom, provided it is rigid. If it is non-rigid, okay, if bonds are assumed to oscillate, then additional degrees of freedom also will be there. Two or more additional degrees of freedom will come. Okay, but in your syllabus, as I said, we'll assume they are rigid molecules. So 6 degrees of freedom for a polyatomic gas. Okay, but let me just mention it. If it is non-rigid, then the degrees of freedom will be more than or equal to 8. Okay. 6 will be there, 3 translational, 3 rotational. Then for every bond that can vibrate, 2 more additional degrees of freedom will get added. So 6 plus 2, 6 plus 4, 6 plus 6. So any number 8 or above is possible. Okay, 8, 10, 12, like that. Okay. Now, why are we talking about degrees of freedom? As I said, degrees of freedom are basically the number of independent ways in which a molecule can store energy. Monatomic gas has three such ways to store energy. Diatomic gas has five. Polyatomic gas has six. Okay. Now, there is a scientist called Maxwell. What he said is that on average, okay, if you take a large number of gas molecules, obviously, when you fill a container with gas, there will be a huge number of gas molecules in it. Okay. So what Maxwell found out or proved theoretically is that on average, Like gas molecules store energy. Some of them may be having more kinetic energy. Some of them may be having more rotational energy. Some of them may be having more kinetic energy due to motion in x direction compared to y and z. Some of them may be having more rotational energy due to rotation about x-axis compared to y-axis and z-axis. So we cannot say it is completely a random distribution, right? But what Maxwell found out is if we average the total energy of a gas, okay, statistically he has done that. If we average the total energy of a gas, we find that the average energy stored per degree of freedom is the same. Okay, that is what is called as Maxwell's law of equipartition of energy. What does it state? On average, the energy stored per each degree of freedom is the same. Okay, it doesn't mean every molecule stores the same amount of energy in every degree of freedom. No, some molecules may be having velocity only in x direction. So they have only kinetic energy due to translation along the x direction. They don't have kinetic energy due to Vy. They don't have kinetic energy due to Vz. That could be happening with some molecules. But some molecules may only be having energy due to velocity in the y direction, right? So if you average it for all the molecules that are present in a container, you will see that the energy stored per each degree of freedom is the same. Okay. And how much is it? It is equal to, he even gave an expression for how much energy is stored with each degree of freedom. Okay, it is equal to half k T, where k is called Boltzmann's constant. Okay, you don't have to remember its numerical value. They'll give you that in the question paper. Okay, the energy associated with each degree of freedom on average is this much per degree of freedom. So this is very useful. This will help us calculate the total internal energy of a gas. If you know how much energy is stored per degree of freedom, then based on the number of degrees of freedom, you can tell the total amount of energy. Okay. So that is why this is very important. So each degree of freedom stores an energy of half kT, where K is called Boltzmann's constant. Okay. Then how much energy will each molecule store on average? Suppose a molecule has F degrees of freedom. Okay. Depending on the type of molecule, it could have 3 or 5 or 6. Okay. Let's call it as F. Then the energy stored per each molecule will be F times of half kT. Because if each degree of freedom can store half kT, then F degrees of freedom can store F times of half kT. That is F by 2 kT. That's the energy present per molecule. Okay. Then how much energy does each mole of a gas store? One mole is Avogadro number of molecules. Now each molecule is storing F by 2 kT amount of energy. And to make up one mole, you need to multiply that with Avogadro number. There'll be those many molecules. So this is the energy stored per mole. Now K is Boltzmann constant. Na is Avogadro number. K multiplied with Na becomes R, which is what we call as universal gas constant. That is the R that you see in PV is equal to nRT. Okay, this is called universal gas constant and its value is approximately 8.314. 8.31, I think, okay, close to that only, 8.314 joule per mole per Kelvin. In SI units, it is this much. Okay, so we can say that each mole of a gas stores an energy of F by 2 RT. Okay. If each mole stores this much energy, then n moles of a gas will store an energy of F by 2 nRT. Okay. Very, very useful equation, particularly in this chapter and even in chemistry. So what have we finally arrived at? We have found out, or we now have an expression for the total energy stored in a gas, total internal energy stored in a gas. Therefore, internal energy, that is U, okay, of a gas is equal to F by 2 nRT. U is equal to F by 2 nRT, where F is the number of degrees of freedom of that gas. So depending on whether it is monatomic, diatomic, or polyatomic, you can decide how much is F. N is the number of moles, R is universal gas constant, and T is the temperature. Okay. Now the aim was to derive ideal gas equation. PV is equal to nRT. First, what we did in the first half of this class, we derived a relation between pressure and speed of gas molecules. PV is equal to 1 by 3 mnv square. That's the relation between pressure and speed. Next, we discussed how energy of the gas molecules is related to temperature. This is the total energy of gas molecule in terms of its temperature. Okay. Now, we derived pressure in terms of speed. Speed is basically translation. Due to rotation, a molecule doesn't undergo collisions. Okay. Due to translation only, it collides with the walls of the container. So, see, we know that each degree of freedom stores an energy of half kT. Then, total translational kinetic energy of a molecule. See, whether it is monatomic, diatomic, or polyatomic, all molecules have three translational degrees of freedom. So the total translational kinetic energy of a molecule, which is basically half mv square, will be 3 by 2 kT. Why is it 3 by 2 kT? Because any kind of molecule, be it monatomic, diatomic, or polyatomic, linear, non-linear, doesn't matter, has three translational degrees of freedom. Per degree of freedom, the energy stored is half kT. So for 3 degrees of freedom, it will be 3 by 2 kT. So the translational kinetic energy of a molecule, on average, you can see. So I'll have to put, you can say, so I'll have to put angular brackets here. Average translational kinetic energy of a molecule can be expressed as 3 by 2 kT. Okay, cancel the 2's. So you can write average of V square for all the molecules of the gas is 3 kT divided by small m, where small m is the mass of the gas molecule. We will put this back in that pressure equation that we had derived first. The pressure equation that we had derived was like this. PV is equal to 1 by 3 capital M, where capital M is the molecular weight of the gas, N, where N is the number of moles of the gas. Okay, PV is equal to 1 by 3 Mn average of V square. So let's write that here, Mn average of V square. And in place of average of V square, we are going to substitute 3 kT by M. So see what this becomes. 1 by 3 capital M is molecular weight, N is number of moles. Average of V square is 3 kT divided by small m. Okay, now the 3's cancel. That's fine. Small m is the mass of one molecule. Capital M is molecular weight. Molecular weight is the mass of Avogadro number of molecules, which is small m multiplied with Na. Okay, mass of one molecule multiplied with Avogadro number becomes molecular weight. Okay, now the small m's can be cancelled. What do you have left? PV is equal to small n Avogadro number Boltzmann constant T. And Avogadro number multiplied with Boltzmann constant is nothing but universal gas constant. That is how you get the ideal gas equation. So basically what we discussed in this class is the proof or the derivation of ideal gas equation. PV is equal to nRT. It's also called as equation of state. What do we mean by equation of state? Pressure, volume, and temperature are the indicators of state of a gas. In what state is it present? Okay, or you will get to know the properties of the gas based on its pressure, volume, and temperature. So P, V, and T, pressure, volume, and temperature of a gas, are called its state variables. Okay, and since this is a relation between state variables, we call it as equation of state. PV is equal to nRT. So the important ideas in today's class would be how pressure is related to speed of gas molecules. Okay, PV is equal to 1 by 3 mnv square, this equation. Another important idea is Maxwell's law of equipartition of energy. So you need to know what are degrees of freedom. Monoatomic gas has 3 degrees of freedom, diatomic gas has 5 degrees of freedom, and polyatomic gas, nonlinear, has 6 degrees of freedom. Based on number of degrees of freedom, you can tell how much energy the gas has. Okay, so you know how to write internal energy of a gas. And by relating these two, you get the ideal gas equation. Okay, so PV is equal to nRT and internal energy is F by 2 nRT. These will be the takeaways from today's class. Right. Tomorrow's class, we will discuss basic thermodynamics. As I said, thermodynamics deals with the conversion of heat to work. Okay. And the system we use for most efficient conversion of heat to work is a gas. We supply heat to the gas expands. In that process of expansion, if it pushes on something, if it displaces something, it will do work. Force displacement give you work, right? So that is the idea behind conversion of heat to work. So tomorrow's class will discuss the different processes by which heat can be converted to work. Okay. Thank you all. We'll continue tomorrow.
Thank you, sir.